kind of a nice fun one. I like this one. Hopefully it comes across. Okay, so we're going to talk about logarithms. So we're going to need those calculators again. So let me grab mine really quickly. Okay. All right, I am set. So logarithms are just exponents, you guys. That's all they are. They're just exponents. So if you see a log, quite often you'll just rewrite it as an exponent. So for example, I had my teacher that called this the hook method. You're going to start with the base, this bottom number, the little number. You're going to go across the equal sign, and you're going to say, okay, b to the y, and you're going to come back across the equal sign, equals x. So these two things are equivalent. So a log is just an exponent, guys. That's it. Don't freak out when you see it. It's just an exponent, okay? So start with the base, cross the equal sign, and come back. And then sometimes it might be this way, so I don't want you guys to think that you always go to the left. Start with the base, cross the equal sign, and come back, okay? So sometimes you'll go to the left, like we did on this top case, we went to the left. Sometimes you'll go to the right. You just got to know, always start with that bottom number, that little bottom number, the base, okay? So these are called logarithms, okay? So let's do a few of these. Write each equation in exponential form. So they're all logarithms. They want us to rewrite them as exponents. So here we go. We're going to use the hook method. So we're going to start with the base, 4 to the second power equals 16. Now don't just go off of, well, I'm just going to write down the thing that makes sense. I mean, it's good to check and make sure it makes sense, but sometimes they'll have all letters here, you guys. So you can't just go, well, 4 squared is 16, so that's how I'm going to write it. They might have A, B's, and C's here. So you got to make sure you understand the process, okay? And yeah, it looks good because it's true, so that one looks good. Okay, we're going to start with the base. We're going to cross the equal sign. So 5 to the negative first equals 0.2. And that one's not as obvious, huh? So let's just kind of walk through it again. I think after last class's lecture, this might be a little bit fresh in our minds. If we're going to check this, we know that 5 to the negative 1 means 1 over 5 to the positive 1, aka 1/5. Well, if you put 1/5 in a calculator, if you do 1 divided by 5, guess what you're going to get? 0.20 or 0.2. Okay, so he checks out. Number 3, start with the base. So 8 to the 0 equals 1. And yeah, anything to the 0 power is 1. So that one's an easy one to check. Let's do number 4. So 23, start there. 23 to the 0 power equals 1. And again, anything to the 0 power is 1. Okay. So now we're probably going to end up going the other way. So instead of going from a logarithm to an exponential, we're going to start off with an exponential and we're going to go to a log. Okay. So basically, we just have to remember, you know, we have these 3 positions, right, that we got to fill in. We have this lower number, right? Okay. So remember that that's the base. So this is the base, the 2, and this is the exponent, right? Okay. So I'm going to go ahead and put in the base, which is 2. I'm going to cross the equal sign to put the 4, and I'll put the 16 here. So you can always reuse the hook method to see if it worked. 2 to the 4th power equals 16. Yep, that worked out. There's our answer. Okay, let's try another one. So we know the base, 27, is going to be the base. So make them the low one. Cross the equal sign for the 1/3 and come back for the 3. So if we wanted to check this using the hook method, let's see. 27 to the 1/3 power equals 3 is exactly correct. Okay, last one. Log, we're going to start with the base. So 1/4 is the base. We're going to cross the equal sign, and then we're going to come back to put the -2. So let's see if this one's correct. 1/4 to the, oh, I messed it up, didn't I? A good thing I'm checking myself. The -2 needs to go here, huh, guys? Oof, now you know why I always check myself. Okay, take 2. 1/4 to the -2nd power equals 16. There it is. All right, you guys, how do we feel about these? This whole hook method. Awesome. Okay, so a log is just an exponent. That's all it is. Okay, so we want to get really good at evaluating these logs to where we're basically just doing them in our head. We're that good. So we'll do a bunch of these throughout the class today, and I think by the end you'll be able to just quickly do it. But every time for the class today, I'm going to type out the question, what the question is that we're supposed to ask ourselves. So the question here is 12 to the what power is 144? That's what this is really asking you guys. Remember we said a log is really an exponent? Well, there you go. 12 to the what power is 144? And I'm going to visually write it out too. 12 to the what is 144? And another way to think of that is, if I put in equals x over here, and I did the hook method, it'd be 12 to the what, 12 to the x, equals 144. So that's another way to look at it. Yeah, you got it. So the answer is 2. Okay, let me put some little, oops, what am I doing? This. Okay, let me put some dividing lines, you guys, really quickly so we can tell the difference here. Okay. All right, I'm going to type the question out again. So the question this time is 64 to the what power? This is tougher. Oh, that's way too big. Okay, 64 to the what power is 8. That's kind of a tougher question for sure. So let's just kind of sit with that for a bit. Okay, so 64 to the what is 8? Yeah, it's got to be something that makes it smaller, huh? Joe's got 1/2 over there. Let's think about that. So if it is 1/2, so this is us checking that. Do we remember what 64 to the 1/2 power means, you guys? What does a fractional exponent mean? Yeah, it's a root. In this case, a square root. Remember we said the root is always the denominator. We said a plant's roots grow in the ground. We said this a long time ago, I think, but that was our little hint to help us remember. A plant's roots grow in the ground. Grow in the ground. So that helps us remember that when we have the fraction, you guys, it's the bottom. The ground, the bottom, that's going to be the root. Okay. So Joe was right. It is going to be 1/2. Okay. So the answer is 1/2. 64 to the 1/2 power is 8. All right. Let's try this one. So let's type out the question because I want you guys to be saying this question in your mind as soon as you see a log. 3 to the, oops. Oh, it made it so I was 3. Okay, I have to type 36. There we go. Okay. 3 to the what power is 1/27. Man, they're just giving us all kinds of tricky ones today, huh? Okay. So if I were to write that out, 3 to the what power is 1/27. Oh, you guys are good. You're fast. -3 is correct. Just really quickly go over it. So for us to check, 3 to the negative third means 1 over 3 to the positive third. And 3 times 3 times 3 is 27. You guys got it. Great job. Okay. Now, your calculator only does 2 logarithms, you guys. It only does log base 10 and log base e. Unless you have like a really cool calculator. There's some people whose calculators can do them all, but most, 9 out of 10 only do these 2. Now these are so common that we don't even write the base anymore, you guys. So it says log base 10, which is called the common logarithm, is actually just written as log of x. It's implied that there's a little 10 there if I don't write it. Okay, so if you don't see anything, it's a 10. Okay. Now log base e, so you watched all those videos on e last time, right? I'm trying to think. Did we do the e together or did you guys watch videos on e? I can't even remember. Felt like we did it together. Oh well. Okay. Together, okay. All right. So log base e actually isn't even written as a log. It's written ln, natural log of x. So this is called the natural logarithm. The other one's called the common logarithm. Okay. So just a little side note, the guy who came up with, he's called the father of logarithms. His last name is Napier. And I'm pretty sure he's French, if I recall. Some sort of Latin-based language. And so, because people always go, why is it written ln instead of nl for natural log? Well, because it's a Latin-based, you know how we say red balloon, but like in French, Italian, and Spanish, they would say balloon red, you guys? So like while we might say natural to describe the logarithm, right? Natural logarithm. They would say logarithm natural. Logarithm natural. So that's why it was shortened to ln. Okay. So don't say ln of x, say natural log of x, because that's how we would read that. Natural log of x. Okay. All right. There we go. This is how nerdy a lot of my friends are, and me included. My friend went to Scotland and she was just like, for some reason, going through a cemetery, and she saw on the outside that Napier was buried there, and she like could not leave the cemetery until she like found his grave in this thing. And she was like sending me pictures of it, like, look, I found Napier's grave. Anyhow, all right. Here we go. None of these have bases, right? But we now know what they are. So we might as well go in and write them, while it's fresh. So log, we know that the base is going to be 10 on that one. So let's put some little 10s down here. Okay. All right. So if I'm going to type out the question for this first one would be 10 to the what power? 10 to the what power is 100. So what would be the answer to that, you guys? Very good. And maybe I'll go ahead and write it like this. And then I see 2 as the answer from you guys. Excellent. Okay, let's try this next one. Boy, let me see if I can make that where it doesn't creep into the next. There we go. And then let me see if I can move it up a little bit. Hey, we fit it. Okay. So the next one's going to be tougher. Oh my. So let's do this one together because it's not at all obvious. Okay. So 10 to the what power is 0.0001. It's hard to answer. So 10 to the what power is 0.123. Okay. All right. Okay. Let's think about that one. So I'm not a big fan of decimals. They're really hard for me to think about this question when it's in decimal form. So apparently not you guys, but for me. So this is like saying 10 to the what power is, and then I'm going to turn them into a fraction. So remember, like back in the day, 4th grade probably, how like this was the 10th place, this was the 100th place, this was the 1000th place. So this would be the 10,000th place. So it's been a long time since you've talked about place value, huh? It's like going way back. But let me just kind of write that out. Tenths, hundredths, thousandths, which means this guy has to be 10 thousandths. Okay. How do you guys get that quickly? Are you guys using calculators? You are, right? That's okay if you are. I just wanted to know how you guys were thinking about it because a bunch of you got that really fast. Okay. Is that how you did it, you guys, with the calculator, or were you just that smooth? Okay, cool. All right, that'll work. So in this case, we know that we need to have a negative because that's the only way to bring it down to the bottom. And then you can see that there's 4 zeros on this guy, right? So if there's 4 zeros, then that means it would be 10 to the 4th that creates 10,000. And you guys know this. Think about 10 squared. You know that's 100, right? So it's 2 zeros because it's squared, you guys. Okay, so you already know this. So my claim is that it has to be 10 to the negative 4th. Okay. All right. So hopefully that made some sense there. Yeah. Okay. I like some people said, this might confuse me though. I'd have to like think opposites, but it works. Okay. So 1, 2, yeah, I don't even see how that actually works on that one. So I'm not going to explain it that way. I think it's a little tougher, but if it works for you, roll with it. Okay. Now, natural log and E, they will always undo each other. So when you see a natural log and an E next to each other like this, you can essentially cross them off, you guys. So it's like, okay, gone. The answer is going to be -3. Same thing here, cross them off, the answer is going to be 10. Now that's super easy math to do, but let's make sure that we understand why. Okay, and this is going to take a while, you guys, to understand why those can cross off. Okay, so the cool thing is it's going to bring back old stuff from like a couple of sections ago. And so it's a nice little review. Okay. So we talked about inverse functions when we talked about one-to-one functions. And we learned that the square root graph, which looks like this, well, you guys already know what the inverse of square rooting is. So in other words, it's like saying what's going to undo square rooting, or what's the opposite of square rooting. So what is the opposite of square rooting? Very good. Squaring. Good. So his inverse function would be x squared, but only half of it because he has to pass the horizontal line test. If I bring this other side in, oh, he doesn't pass the horizontal line test. So I have to make sure I take half of it. And I'm going to take the half that's the reflection of, so there's good old y equals x. Remember how important he was? They always reflect over that line. Okay. So if two functions are inverses of each other, then they undo each other. So what we're saying is that the square root of x squared, those undo each other, or the square root of x squared. So in other words, the order doesn't matter that I do it in. And to get really mathy and much more general than this, you guys actually learned the following. If f and g are inverses, then f compose g of x is x, and g compose f of x is x. And that was actually something that you had to show on some homework problems. You actually had to compose these to make sure they were inverses. Do you guys kind of remember that? Like if you had if you had f is like x squared plus 3, then f inverse, or g, depending on what you want to call it, was the square root of x minus 3. And you could tell that these were inverses because you plugged them into each other. So you took this guy and you plugged them in right there. So that's the square root of x minus 3 squared plus 3 when I plug it in. And the squared and the square root undo each other. And so you have x minus 3 plus 3, and those undo each other. And you got, oh, what'd you get? X out, right? Or similarly, what if we went the other way with it? So what if we plug this guy into that? Then that would be the square root of x squared plus 3 minus 3, right? Well, the plus 3 minus 3 undo each other. The square root of a squared, we get x. Oh, okay. So I hope this lays the foundation for you to understand what I'm about to say now. E to the x is exponential growth. We learned that last time. And natural log of x is his inverse. So here's what e to the x looks like. We learned that last time. And so here is what natural log looks like, you guys. Trying to make this guy look like a reflection over y equals x. I probably didn't do the best job, but good enough. Okay. And let me label this guy as natural log. Now, since these two functions are inverses, then this thing right here must be true in the middle. That must be true. Let me put f's and g's on these guys. So let's call this guy g, and then let's call this guy f. So what does that mean? Well, that means that if I plug e to the x into natural log of x, if I plug e to the x into natural log of x, that I should just get x when all's said and done, according to this theorem right here, right? They undo each other. Or vice versa, what if I plug natural log into e? So if I plug natural log into e, those should undo each other. So what I just said on the last slide was, anytime that you see natural log of e next to each other, you can cross them off. Anytime you see natural log and e next to each other, you can cross them off. Does everybody understand with this slide why we're crossing them off? Inverse functions undo each other, right? And so we just get x when all is said and done. Yeah, so the natural log of e is 1 because the exponent on that e is a 1. So when you go to cross these guys off, there's still that 1 left. Yeah, absolutely, Dean. Okay. All righty. Any other questions? I want to make sure that this is such a big deal, you guys. If you're planning on going on in math, this is going to creep up in every class over and over and over again. It's not going anywhere. That's why, I mean, my calculus students right now are struggling with it because it wasn't a big deal in their 105. It needs to be a big deal here. So does everybody understand that natural log is the inverse of e? So anytime that we do function composition between the two, whether I plug the e into the natural log or I plug the natural log into the exponential, they will always just get you x out. They'll undo each other. You can cross them off. Okay, guys. So this was in reference to these last two. We just crossed the natural log and the e out. That is the same thing as when you have this. We all go, oh, okay, well, those are inverses, and don't we all just kind of cross those off anyways and say x? That is the same concept. Okay. Alrighty, you guys. We'll probably hit it again. Let me actually show you the really pretty graphs, not Mecklenburg's ugly graphs. Although I felt like I did pretty good on that one. Okay, let's see. Let's go to GeoGebra. Okay. Now GeoGebra actually has one of the reasons I like it. Oh, not running it off the internet. You have to download it. So never mind. I'm not going to talk about it. But there's e to the x. I'm going to graph y equals x, so you have it as a reference. And let's graph natural log of x. There you go. Look at that pretty reflection, you guys. Looks beautiful, right? Okay. All right. So these next few are just you using your calculator. But I do like to kind of guess before I start, because that's what reinforces what a log means. If I go to the calculator too soon, then I'm just pushing buttons and like got answers and stuff, and they might be right answers, but I really didn't get anything out of it. So what I'm going to do is I'm going to try to estimate before we start. I think that's kind of fun, and it makes me remember what a log is. Okay. So we said if there's no base and it's log, what's in the bottom? Very good. I'm going to put my little 10s here, you guys. Okay. So the question here is 10 to the what power? 10 to the what power is 200 is the question we want to answer. Well, let's see here. I know 10 to the first is 10. So it's got to be bigger than 1. And I know 10 to the second is 100. Okay, it's got to be bigger than 2. 10 to the third gets me 1,000. Okay, I've gone too far. So it's got to be somewhere in between these two, you guys. It's got to be somewhere in between 2 and 3. And my guess is closer to 2, right? Because it's a little bit closer to 100 than it is to 1,000, you guys. So something closer to 2 is what I would guess. Okay, let's go to our calculators, you guys, and go ahead and hit log of 200. Log of 200, and type in what you get into the chat. Yeah, okay. Now I'm reading the directions and it says round to 4 decimal places. So what would it be if we did 4 decimal places? Ah, very good. So 2.30102. And let's see, 1, 2, 3, 4. So this 2 is going to keep that 0 as 0. So you guys are right. It is 2.301. And that's what we said. We said it's going to be closer to 2 than it is to 3. Doesn't that feel good that you actually knew that before your calculator even spat it out? You're like, oh, it's going to be like maybe 2.3, 2.4, you know? It's good to know what these things mean. Let's try the next one before we go to our calculator. Okay, so the question is 10 to the what power? 10 to the what power is 0.074. Okay, well, I know 10 to the first is going to be 10. That's too big, so let me not even do that one. How about 10 to the 0 power? What's that? 1? Okay, we're still too big. Let me try 10 to the negative 1. Oops, sorry, you guys. Let me just move this a little bit lower. Oops. Oh, no. Did those get bundled together? Okay. Okay, so let's try 10 to the negative 1. Oh my gosh, Mecklenburg, put your pencil on. Okay. Well, we know that's 1 over 10, which is 1.1, right? That's the 10th place. We're still too big, huh? Let's back it up another one. 10 to the negative 2 would be 1 over 100. So 1/100. So let's see, tenths, hundredths. Okay, we're there. Let me put extra zeros on here because it helps me, you guys, when I have the same amount of decimal digits. Isn't 74 Going to be somewhere in between 10 and 100. 74 is somewhere in between 10 and 100. And it's closer to 100 than it is to 10. So I'm going to guess that we're going to be closer to the -1, you guys, would be my guess. Closer to -1. All right, let's go ahead and go to our calculators and let's see what this guy spits out. I'm thinking -1.2-ish. I don't know. -1.3-ish. And go ahead and type it in, and 4 decimal digits, right? 4 decimal digits. Good, that's definitely closer to -1, huh, than to -2. That looks pretty good. Oh, and I got a second on it. Okay, very good. Okay, so it's -1.13076. And if I go out 4 decimal digits, 1, 2, 3, 4, then 6 is going to round that guy up to an 8, right? So it's going to be there we go. Okay. All right. We'll just go ahead and use our calculators on these other two because E is the base, and that's a little bit too hard to wrap our brain around because E's a decimal, right? 2.7. So let's just use the calculator. Can you guys find the natural log button on there? Let's do natural log of 200. Okay, we got a 5.2983. Good, you guys. Okay, and let's try natural log of 1.005. Oh my goodness, this one's being weird. Okay, I don't know about your guys' calculators because they all give different answers out, but mine is saying this times 10 to the -3rd power. Is anybody else is doing like an E -3 or something like that? Okay, so that means we have to move our decimal place 3 times to the left. So left 3 times. So if I move it to the left, 1, 2, 3, it looks like we're going to get the decimal 0.00498. Now, if I do 4 decimal digits, right? 4 decimal digits, 1, 2, 3, 4. 8's going to round this guy up to a 10, which is going to round this guy up to a 5. So here's going to be our final. Oh my gosh, so many tricks on that one, you guys. So let's recap the tricks. Our calculator gave us scientific notation, huh? So we had to know that either a capital E with a -3 after it or this times 10 to the -3rd means move the decimal place to the left 3 times. So we did that. And then we wrote down 5 numbers because we know we have to round to 4. 8 made the 9 become a 10, so you'll put a 0 there and you carry the extra 1. So that's how we ended up getting 0050. You guys feel okay about that one? Anything I can make clearer on that? Like, would you like another example of it? Okay. So let's say that you plugged it into your calculator and you got, let me see here. There you go. Sorry, I don't know why that was so hard for me. All right. Okay, so what would that be as a decimal? Don't worry about rounding it yet, guys, but what would it be as a decimal? Yeah, very good. So if you move that decimal 2 times to the left, that's going to put a 0 in front of the 3. Yep. So it's going to be 0.039297. So I have to literally draw on top of it. If I don't draw on top of it, I'll have the wrong amount of zeros, you guys. Okay. Alrighty. I don't know why, but stuff like that I'll mess up. Typing stuff into my calculator, I'll have the wrong amount of zeros. So I just have to be super careful that I just don't do stuff like that. Okay, 1, 2, 3, 4, right? So we have 4. So this 9 is going to round this 2 up to a 3, right? So our answer would be 0.0393. Okay. So that's going to happen a lot, you guys, where your calculator is going to spit out scientific notation. So it's good that you know what the heck that means, right? And if it had been 2.69 times 10 to the 5th, the positive 5, okay, well then instead of moving the decimal place to the left, we'll go to the right 5. So 1, 2, 3, 4, 5. Add your zeros in. Oh, that's going to be 269,000. So negative, move it to the left. Positive, move it to the right. And that kind of makes sense in my brain. Okay. Is there an LN button anywhere on your calculator? An LN or an LN of X or an LN of a blank? It's usually pretty close to your E. So if you found E to the X, then your natural log is usually pretty close to E. Sorry, Malcolm, I kind of spaced on that. Did you find it? Okay, great. Cool. Okay. And if you're using your iPhone, remember, turn it sideways and it's got LN on it. Okay, cool. Found it, Makai. Good. All right, you guys. So here's some properties of logarithms that I'm going to actually just slowly go over. Because it's if you just memorize this, you're going to drop it out. You got to understand it, guys. So remember, every logarithm is an exponential. So if we took this logarithm and we rewrote it using the hook method, it start at the base, cross the equal sign, and come back. So it'd be b to the 0 power equals 1. Okay? So yeah, anytime that you have a logarithm with a 1 right here, I'm sorry, with a 0 right here, right? Okay? And a 1 right here, I'm sorry. Anytime that you won't have this side, you guys, you'll just have some number and you'll have a 1. Anytime you see a 1 in this position, you know the answer is going to be 0. Okay? Because of what we just said. What's the question if I didn't have this here? B to the what power is 1? B to the what power is 1? Oh, well, anything to the 0 power is 1. Okay. All right. Over here, this would be if I hook methoded it. B to the first power is B, right? Okay. So anytime that you see a log where these match right here, you know the answer is going to be 1. And just every single time, write down the question, you guys, that I've been writing down. If you don't know this side, this would be B to the what power is B. B to the what power is B. Oh, the only thing I could put in there is a 1, right, to make this true. Okay, so the answer must be 1 to that. So on these first two, just use the hook method and you'll be fine, okay? All right. Over here, these two are exactly what we just talked about a second ago with E and natural log, but they're more generic, they're more general. So if I have any exponential, let's say that I have 2 to the x, you guys, 2 to the x. My claim is that his inverse is going to be log base 2 of x. Those two are inverses of each other. So logarithms are always the inverses of exponentials. Let's just double check it, make sure I'm not lying to you, huh? Let's plug this guy in. Okay, so 2 to the x, let's see. That's exponential growth. You guys already knew what that was going to look like, right? Exponential growth. And now we have log base 2 of x. Oh, let's put y equals x in there just to make sure. Look at how perfect it is. If you change this to a 1/2, it should be decay. What's going on here? How did the x get in the inside? There we go. Okay, so there's our decay. What's going on? I'm sorry, you guys, I keep hitting so many wrong buttons. Okay, so there's our decay. So now I'm going to go ahead and type log base 1/2. Log base 1/2 of x. And look how pretty that is. So no matter what, if you have a exponential of any exponential, right? You know his inverse is going to be a logarithm with that same exact matching number. Okay. All right. All right. Do we have any questions on this, you guys? Okay, so what does that mean if these are inverses? Well, recall that means the following then. If I plug g into f, I get x. And if I plug f into g, I get x. They're going to undo each other. They're going to undo each other. So let's do that really quickly. Let's see what that looks like. Okay, guys, who's getting plugged into who on the f composed g? Ah, very good. You guys remembered. The one on the right gets plugged into the one on the left. Okay, so I'm going to take log base 2 and I'm going to plug it in right there into that x in the exponent. I'm going to plug it into the x in the exponent. Now, does everybody see that that matches? Well, first of all, we know the answer is x, right? Because of what this is saying over here. They undo each other. You can basically just cross those guys off, right, and get rid of them. But what I want you to notice is, doesn't it match this? It does, huh? Okay. Now, the same is true the other way. If I do this bottom one, G compose F, well, now I'm going to take F and plug it into G. So I'm going to take F and I'm going to plug it in right there into G. So that would be log base 2 with a 2 to the x plugged in for the x. And we know the answer should be x according to this over here. Okay, and you'll notice that that is what this one is saying right here. Okay, so knowing that logs and exponentials are inverses of each other is what enables us to go in here and just cross all this junk off. So it enables us to go in here and just cross all this junk off and leave the x. Okay, let's practice a few. Okay, so we'll just hook method these instead of memorizing the theorem. Hook method works, so let's use it. Okay, so the question here would be 19 to the what power? is 19? What do you guys think? Very good. 19 to the what power is 19? Well, that guy would have to be 1, huh? It's the only way to make it work. Excellent. What's my base on this next one? I didn't write it. Oh, good job. So the question here would be 10 to the what power is 10? 1 again. Very good. Okay. 1 again. So 10, oops. 10 to the what power is 10? And you guys are saying 1 again. Okay. All right. Same thing here. What's my base on this one? Yeah, natural log is base E. Base E. So the question here is e to the what power? E to the what power is E. And it's 1 again. So the moral of the story here is e to the what power is E? Well, x would have to be 1. So the moral of the story here is if we see these matching, right? If we see these matching, then we know that the answer is going to be 1 on that, you guys. Let's try some more. Okay. Okay. So the question is 273 to the what power is 1? 273 to the what power is 1? I'm getting a lot of zeros. Very good. Yep. Anything to the 0 power is 1. Excellent. So this one would be 1/8 to the what power is 1? 1/8 to the what power equals 1. 0 again. Good. So what we want to take away from that is anytime we see 1 in this position, we know that the answer is going to be 0. Or just use the hook. It's probably easier, less to memorize. Okay, this is using those last ones. Does everybody see that this is an exponential? The 10's in the exponent, right? So it's like an exponential. And this is a logarithm right here, right? So pretend that you knew that f were like log base 30 of x, and you knew g was 30 to the x. What we've done is we plugged the exponential into the logarithm. If we did that, it would look like this, log base 30, and instead of this x, I'm going to put 30 to the x in its place. And we know anytime we compose a log with an exponential, they undo each other and just give us x out. They undo each other. So we could like literally go up here and just like cross these guys off, right? We could just cross them off. Okay. So with that knowledge, we could do that here. We can just say rant. Guess what the answer is? Yep, it is 10. So anytime that you see that an exponential has been plugged into a log or a log's been plugged in to an exponential, just cross them off. They're going to undo each other, you guys, and only the 10 will remain. All righty. And all of these are those cases. I have taken an exponential. This is an exponential because the 12's in the exponent, right? I've taken an exponential, and what have I plugged it into? I've plugged it into a log. So we can just say these are gone. Natural log of e undo each other. It's -12. This is the other way around. We've taken a log with base 10 and we've plugged it into an exponential. Same thing over here. I've taken a log base 8 and I plugged it into an exponential. So let's make sure everybody sees that. If I have 10 to the x and I have log base 10 of x, I have taken the log and I have plugged it in right there so that it becomes 10 to the log. And anytime that we compose an exponential with a log, they're gonna undo each other, you guys. You know, I'm gonna put that back. I'm just gonna move it down here. Okay, they're gonna undo each other. So I'm basically just gonna cross this stuff off and only the 14 remains. I'm just gonna cross this stuff off and only the 5 remains. Now they do have to have the same base. If somebody's like, okay, well here's an exponential and I plugged a log into it, right? Well, this one has 2 and this one has 3. Those aren't gonna undo each other. 2 to the x's inverse isn't log base 3 of x. 2 to the x's inverse is log base 2 of x, okay? But you'll notice that on all of our problems, right? Let me put them back so we can see them. The bases match. This is base 10 and it's log base 10. This is base 8 and it's log base 8. So that's what enables us to just go in there and just completely annihilate and say, they're gonna undo each other. They're gonna undo each other. Do you guys feel comfortable on those last two? Okay, great. Okay. So there's lots of different ways to graph logarithms. It looks like they're trying to guide us through one way, so let's do it the way they're trying to guide us, okay? It says rewrite into exponential form and select values for y. So, I mean, written like this, yeah, it could be a little intimidating to t-chart that guy, right? It's like, oh, if they don't match, they wouldn't give you that, to be quite honest. You'd have to use like a calculator or technology, so they probably wouldn't give it to you, Alexis. That's a great question. What do I do if they don't match, huh? Okay. Now, let's see here. So let's say that I like your question so much, I'm going to continue on with it. If I have, let me do this. Okay. So let's say that they gave you one like this where the 2 and the 10 don't match. Then you can use your calculator if it's base 10. Remember, your calculator only does base e and base 10. So I gave you guys a base 10 so we could. So you could like plug this guy into your calculator. So let me see what log of 5 is. I'm getting approximately 0.69897. And then I could do that math and do 2 to that power. But they probably will never give you that, Alexis, but it is doable. So it's a great question. I just haven't seen those show up on your guys' your homework assignments. They're more interested in you knowing the property, believe it or not. Yeah, that's a great question though. Okay, and guess what? Later on in the class, we're gonna learn how to compute on our calculator. Stuff that isn't base 10 and isn't base E. Like you'll be able to do a base 3 because we're gonna have a formula that changes the base. So it might start off with the base 3, but by the change of base formula, you can change it to base 10s. And so now you actually can compute that on your calculator. So that's coming. So if you don't have a super cool calculator that does every base, like some people have a cool calculator, you guys, where it has this button, okay, where you can input the base and you can input the argument. But if you don't worry, we've got the change of base formula for that, okay? All right, so back to this problem. It could be really intimidating to t-chart it when it's written like a logarithm like that. So we said logs are just exponents. All right, let's write this guy as an exponential then. So as an exponential, let me move this up higher so I don't start creeping into our work. As an exponential, the equation would become, let's hook method it, 3 to the y power equals x. So start at the base, cross the equal sign, and then come back. So 3 to the y power equals x. Now, the next part of the direction says select values for y. Well, that makes sense. I don't want to select x values. Like, let's say I select an x value. It's like, how the heck am I going to figure out what y is? Right? That's going to be too hard for me. So instead of selecting x's, I'm going to select y's, because if I know the y values and I put those in, I can do that math and find the x. So does it make sense, you guys, that I don't want to be plugging stuff into the right-hand side of this? That'd be too hard to solve. I'd way rather plug something in for the y, because then that'll be easy math. So this is going to feel weird, but we're going to actually pick the y values. So let's say we pick -2, -1, 0, 1, 2. Okay. So let's go ahead and substitute each one of those in for the y. Oh, we can do 3 to the third. It looks like our graph paper is going to actually hold it, so let's do it. Okay, so we're plugging them in for the y. Let's do the math. We know that 3 to the -2 is 1 over 3 to the +2. So 1/9. We know that that's really 1 over 3 to the +1st. So 1/3. Anything the 0 power is totally not 0, it's 1. And then these are easy for you guys. You've been doing these for years. Okay. Okay, let's go in here and graph these. And so they already graphed it. Let's just make sure that we have the right points, okay? So 1/9, -2. Going over 1/9 would be like nothing, you guys, because they're counting by threes. So over 1/9 down 2, that's going to be this dot. Then I'm going to go over 1/3. That's still nothing. And then down 1. So this is the over 1/3 down 1 point. Then 1, 0 must be this one. And that looks like that's about 1 if I'm counting by threes, huh? 3, 1, finally something on a corner, cool. 9, 2, also on a corner, beautiful. And 27, 3. Okay, this looks great. So do you guys have any questions on this process for graphing a logarithm? Let's recap it. We don't think of it as a logarithm. We think of it as exponential. And the weird part is we don't pick x's, we pick y's. That's the weird part. Alrighty. So now let's say, let's go ahead and rewrite this guy a little bit better. Trying to look at what they want. Okay. I'm going to rewrite them like this. Okay. So I just switched the order on the 1 plus x because I think that we're used to looking at it as x plus 1. Okay. All right. Now, this one's not going to be as pretty if we were to try to like write it as an exponential. It'd be 2 to the y power equals, I wouldn't even be that. We got this plus 2 ruining it, huh? You'd have to like move the 2 over. I mean, this just isn't looking very easy. Okay, so let's talk about how we graph this. So here's what we do, you guys. We try to figure out what the parent function is. That's the first thing we do. Is we say, what's the parent function? Remember, the parent function is the simplest function of that type. take away all the translations and reflections. So if I were to take away all the translations and reflections, I'm going to take away this translation, and I'm going to take away this translation, and it just gets me log base 2 of x. So y equals log base 2 of x is the parent function. Okay. Let me put those back really quickly. How do you guys feel about picking out the parent function? Would you be able to take this complicated one and go, okay, that's his parent function? Let me give you another one. Okay. So I got to get rid of the translations. This is to the right one. This is down 2. I've got to get rid of the reflection. So I got to get rid of that negative sign. And I got to get rid of the stretching and the shrinking. So the bare bones, the simplest function of that type would just be a log base 3 of x. Okay. One more. And this time you guys tell me. What would be the parent function? Very good, you guys. Yep. Get rid of the 3. That's the stretch. Get rid of the shift to the left and the shift down. Yeah, so no, it wouldn't work, Malcolm. It actually is technically incorrect. You can't use the hook method when you have that 2 being added. Okay, so I can't use the hook method as is, like I can't do it right now, okay? I'd have to move the 2 over to the other side to join the y. And then I would be allowed to do the hook method because you have to isolate the logarithm first. So we isolated the logarithm, so now I could do the hook method. So I could say 2 to the y minus 2 equals x plus 1. That would work. 2 to the y minus 2 equals x plus 1. But I'm still looking at that and thinking that that's not like super easy to do. It could be done though. It can be done. So the reason why I'm teaching you this way is because I can tell by the directions that they've given you that they want us to use shifts and stuff, you guys. So that's the reason why I'm doing it that way. But you're right, Malcolm. We could just do what we did on the last one and t-chart it as the exponential. But I'm pretty sure Connect is going to ask you some questions like, which way should we shift it? You know what I mean? So I got to get you ready for those homework problems. Okay, so step 1, we don't like 1 plus x. We like x plus 1 better. Step 2, what would be the parent function of all this madness? Like, what's the simpler one? Oh, it's just log base 2. Now we're going to rewrite this guy as an exponential. So it's going to be using the hook method. 2 to the y power equals x. 2 to the y power equals x. And we're going to pick y values. We're going to pick y values. And let's go ahead and plug those in, and we can do this really quickly. That's the benefit of writing the parent function. This is easy. All right, so I'm going to do 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the 1, 2 to the 2. Okay, 2 to the negative 2 is 1 over 2 to the positive 2. So a fourth. 2 to the negative 1 is 1 over 2 to the positive 1. So a half. Anything to the 0 power is 1. 2 to the first is 2. And 2 to the second is 4. All right. Now I'm going to graph these. Okay? But these are not the function, the final function. Okay? So this is just our parent function. So here we go. I'm going to go over a quarter, down 2. I'm going to go over a half, down 1. I'm going to go over 1, 0. Over 2, up 1. And over 4, up 2. Okay. So this I'm going to make dotted to let the reader know, hey, this isn't the final answer. This is my in-between scratch work. Okay. And now all we have to do, you guys, is just pick these up and move them. That's it. So let's figure out how we have to move it. So which way would we move it because of this +1? Yeah, that's the one that's lying. Remember, change it, don't change it. Change it, don't change it. So this one's really going to be left 1. And this one's going to be very good. Up 2. Left 1, up 2. So here we go. We're going to pick up every point, and I'm going to go left 1, up 2, and I'll show it to you. Let me start with these ones on the corner. I'm going to go left 1, up 1, 2. Bam, that's where I landed. Perfect. I'm going to go left 1, up 1, 2. Yay, I got that point. I'm going to go left 1, up 1, 2, and I got to that point. So what if we skipped over one of the points? It doesn't really matter, because on Connect Math, you probably only need 2 to 3 anyways, right? And it'll do the curve for you. Here's left 1. Remember, a half a square is half. Another half would make a whole. And then go up 1, 2, bam. Okay? So let's recap the second half of it. Once you got the parent function and you wrote them as an exponential, you picked y values, and this was such easy math to do. Look how quickly we blazed through that. And so then you just graph those points, knowing that that's not the final answer. That's log base 2 of x. The final answer is log base 2 of x plus 1 plus 2, right? So you got to figure out, well, how do I shift that parent function? Okay, this one's the one that's lying, so instead of right 1, it's left 1. This is the one that's telling the truth, so I'm going to go up 2. So I'm going to go left 1, up 2, left 1, up 2 with every single point on that green graph. And bam, I got my final answer. So why do we use the parent functions? They're simpler. It's a much easier function to look at. This thing's easy versus that one we had written a second ago that had all those other numbers in it. Okay. All right. How do we feel about that one, you guys? Any questions? Oh. Okay, it said my internet was unstable. So I'm just checking in to make sure that there's no more questions on this one. Do you guys have any questions? Something I can clear up? Okay. All right. We'll do this last bit, and then, oh, I just asked if there were any questions. My internet cut out. Okay. All right. So what I want to do here is I actually want to insert a slide so we're not looking at this because that's going to give us the answers. Okay. What I want to do is I want to graph really quickly b to the x. Just a sketch. I don't have to be too detailed. Oops. Okay. So let's say that that is b to the x. And from watching the videos, you guys know that, or maybe this was with me, b has to be greater than 1. Okay. B has to be greater than 1. Why? Because it's exponential growth. And we found out that the only numbers that grow are numbers bigger than 1, right? Okay. All right. So let's write down a few properties about this guy. Let's get his domain, his range, the asymptote, and 1 point on the graph. Sorry, I'm getting on the edge of my Surface Pro and it's hard to write. Okay. And this is for b to the x. All right. So the domain, that means left and right. Well, this arrow, it's going to keep going to the left forever. And it's going to keep going to the right forever, just slowly, but it is going to keep going to the right really slow, huh? Okay. So if it's going to go to the left forever and it's going to go to the right forever, negative infinity to infinity. Now the range, not so. What do you guys think is the lowest value, the lowest y value? Okay, it's good guesses. This is where 1 is, you guys, right here, right? So it does look like I have some lower. So give me a second guess because you're close. You're super close. I don't even know sometimes if you guys can see what I'm drawing. So there are some lower than 1. All of these are lower than 1, huh? You guys see that? So what do we think would be the lowest? Yeah, 0. And here's how I'm going to take care of the fact that it's not going to be 0, which I can tell is why some of you were like, I'm going to put a parentheses on it. So it is never going to be 0, and I probably didn't do the most spectacular job of drawing this. What's happening here is this is an asymptote that it's going to get closer and closer and closer to as time goes on, you guys. Now I claim it'll never be 0. That's why I put a parentheses on it. Think about it. If I have 3 with an exponent, there's no way for me to make that guy 0. If I throw negatives in there, it just makes fractions. If I throw positives in there, that's not going to be 0. If I throw 0 in there, it gets me 1, right? So I'm never going to get 0 out of that, you guys. And as I go further and further this way, you know, like maybe -5, negative 10, whatever, all that's going to do, let's say I went all the way to -100. That's just going to be 1/3 to the positive 100. It's going to be close to 0. Gosh, I think my calculator might explode if I tried to do that. Let me see what it tells me. So I think it's going to be like, nope, I'm not doing that. Oh, it says math error. What's up with that? Can't handle it. Oh, that's because I typed 300. Okay, let me see if it'll handle it when I type 100. Oh my gosh, you guys, look what it gave me. At least we all know what that means now, huh? I have to move my decimal 48 times this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? It's just going to be like 0.000000000, right? So it's close to 0, but it isn't ever going to be 0. That's why you guys see that it's just getting smaller and smaller and smaller. Okay, over here. Okay. So does everybody feel okay with the fact that exponentials, like this guy, x is in the exponent, so it's an exponential, will never be 0, but can get really close to 0? You're okay with that? Okay. All righty. I got no answer, so I'm just going to assume you're okay with it. Okay. All right, now how about the highest? We got the lowest y value. It's getting closer and closer to 0. How about the highest? Infinity. Good, you guys. Okay, so the asymptote is this guy, right here. So what's the equation? Oops, what am I doing? What's the equation for that, you guys? The x-axis. What is the equation for the x-axis? It's a tricky one. That's why I'm asking. What's the equation for the x-axis? Okay, not sure. Very good. Y equals 0. People mess that up because they want to put x equals 0 for the x-axis. Y equals 0. Okay, well, there's really only one point I expect you guys to know, and it's that guy. So 0, 1 is the one point that everybody knows on an exponential, and it's on them all because I don't care what the base is. I don't care if the base is a half, if the base is 3. I don't care if the base is 500. Anything to the 0 power is? One, 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 yeah. So that means that 0, 1 is going to lie on all of these, you guys. If you plug in a 0, you'll get a 1 out. That's why they all go through that point. Okay. So now what we want to compare that to is his inverse. Ooh, I'm hoping that everybody knows the inverse of b to the x. Ooh, this is going to be a good quiz right now. Let's see what you guys think the inverse of b to the x is. Inverse of b to the x. You know what? I probably should have done it on the same graph, but maybe I'll do this. Oh, it's linked. There we go. Oh, no, I'll get there eventually. Okay. Okay, I'm trying to give you guys some time to think about what the inverse of b to the x would be. What do we say the inverse of exponentials is? Or are, is, inverse is, yeah. What undoes an exponential? Okay, a lot of us aren't sure, huh? No one's answering. So let's go back. Remember we said that if 2 to the x is my function, then log base 2 of x would be his inverse, right? And we even did it for e too. We said, hey, e to the x, if that's my function over here on the right, that's an exponential, then log base e, natural log, is his inverse. So if we want to know what the inverse is of b to the x, it's going to be log base b of x. That's going to be his inverse. Okay, so I'm going to graph e to the x really quickly. B to the x, sorry. And now I have to try to reflect that, you guys, over this line. If I do that, it looks like I'll get this green graph. And you guys just said, or we just said, that's log base b. These are inverses of each other. Okay. Now, without even looking at that graph, we don't need them. So don't even look at them. I claim that you should be able to answer all of these questions without looking at that green graph. So let me just draw your attention to something you guys learned this chapter too. This is why this is so good. We're reviewing so many old things. It's beautiful. We need these reviews for the final. Recall that for inverse functions, x and y switch. Do you guys remember that when you were finding inverse functions, like one of the steps was to literally switch x and y? And then we also showed that if I have a graph and I have the point, let's say 2, 2, 1, so 2, 1, and I reflect that over y equals x, that should go to 1, 2. I didn't do a very good drawing right there of y equals x, but can you guys kind of see that it does look like this point would go to that point if I folded the paper on that line? So if I folded it across this line, 2, 1 would go to 1, 2. You guys are quiet. Do you guys remember switching the x and the y for inverses? Yeah, okay. All right. So if the x and the y switch, isn't x the domain? If he switches, that means he's going to become the new y values, the new range. And these y values must become the new x values. So we can just literally switch those and put the negative infinity to infinity in the range spot and the 0 to infinity in the domain. But let's check and see if that looks good. So what do you guys think about the green graph? If I'm looking at the green, I should have done this all in green, huh? Ugh, too late now. But if I look at just the green graph, so let me just erase this guy out for a second. I'll put him back later. Do the x's look like they're 0 and up? Like I definitely don't have any negative x's, huh? And I claim I don't even have 0 because it looks like it's an asymptote. So 0 to infinity. Now, because the y values go down forever and are going up forever, just slowly, negative infinity to infinity for our y values. This is looking great. Now, if you take a horizontal line and you reflect it over y equals x, you're going to get a vertical line. I don't know if you guys can tell that this line would reflect to this line. Okay. So all horizontal asymptotes will become vertical asymptotes. So that means instead of the x-axis, it should become the y-axis, which is x equals 0. Okay. Let me really quickly put this guy back. This is the x. Oh, I keep writing 0 on anymore. And this is y. And finally, if 0, 1 is on b to the x, then what point is going to lie on log base b of x? Nailed it. Switch them. Perfect, you guys. Well, you can kind of see that if this one's 0, 1, then yeah, this looks like this could be 1, 0. Yeah. Okay. So that's all recorded right here, you know, all that stuff. But now it's kind of us really diving in deep and understanding why those are the way they are. Okay. So let's see here. Can you guys hear me? Yeah, okay. All right. So give the domain and range in interval notation, write an equation of the vertical asymptote. So to find the domain, you're always going to take the stuff inside the parentheses and make sure it's strictly greater than 0. Okay? So to find the domain, to find the domain, take the stuff inside the parentheses and set it greater than or equal, oh, no, greater than 0. Okay, so in this case, we're going to make x plus 3 greater than 0. So we solve that and we take away 3 from both sides. We just get that x is greater than -3. Now they gave you a graph. This is if you don't have the graph, you guys. This is how you do it. Okay, now you can see that that is indeed true. Here at -3, it looks like there's a vertical asymptote, right? And so all the values are going to be greater than -3. Okay, so there's a vertical asymptote at x equals -3. Okay, now, why do we do that? So guys, pull out your calculators really quickly for me. And I want you to try to take the log of 0. And I want you to try to take the log of -2. So can you pull those out? Let's go log of 0 and see what you guys get. Error? Me too. Math error is what mine says. Okay, good. Try the log of -2. Same thing? Okay. So that's why this should make sense. What we're doing up here is we're saying, well, I got to make sure that that stuff is greater than 0. Because I can't take the log of a negative. I can't take the log of 0. So it has to be strictly greater than 0, not even greater than or equal to. Because we just said we can't log 0. So I got to take 0 out, you guys. I got to make sure it's strictly greater than 0. Does that make sense? That stuff inside the parentheses better be positive, or else I'm not going to be able to log it. Okay, so that's going to be our domain. Now let's go in here and get our range. So the range, well, it goes down forever and it goes up, up forever. It's just slowly going to go up, right? So that means it's going to be from -infinity to infinity. Okay, let's try one more of those to really seal the deal. Okay. So we're going to go ahead to get the domain. We're going to set the stuff inside greater than 0, right? So that means that x has to be greater than 0. And if you look at your picture, you can indeed see that right here at 0 is a vertical asymptote, and all of the graph is on the greater side. So x equals 0 is going to be our vertical asymptote. Okay. Now let's go in here and get our range. So the range, let's see here. It's going to go down forever. It's going to go up forever. So -infinity to infinity, always for logarithms, always. Okay. Oops, I didn't use interval notation. Let me go in here and do interval notation, you guys. I just realized that. So greater than -3 would mean -3 to infinity. And then for the domain, greater than 0 would mean 0 to infinity. Okay. Okay, here we go. The absolute magnitude m of a star is the apparent magnitude, little m, a star would have if it were placed 10 parsecs from the Earth. The lower the value of the magnitude, the brighter the star. Our sun has an apparent magnitude of negative 26.74. The brightest star in our night sky, Sirius, has an apparent magnitude of negative 1.44. Okay, so the lower the number, the brighter. So that makes sense. It's saying the sun, we know is the brightest, is negative 26, while the next brightest is negative 1.44. Okay, so that makes sense. All right, now we got this formula here. The formula relates to stars' absolute magnitude, apparent magnitude, and its distance d. Okay, so I'm going to label all these variables. I got to know what they stand for. Okay. All right. If Sirius is 2.637 parsecs from the Earth, and the sun is 4.887 times 10 to the negative 6 parsecs from the Earth, what is the absolute magnitude of each star? Okay, so while I'm typing stuff, I want you guys to think about what they just gave you right here. See if you would be able to tell what letter you would plug that in for. So I'll give you a minute while I type some stuff. Okay. All right. So what do we think, you guys? We have 3 different letters. We've got big M, little m, and D, right? So we just have to figure out what that 2.637 is going to go in for. So I'm going to give you some time to read. Okay, so there's a lot going on here to read, huh? Okay. So because it's got parsecs on it, you guys see that? And it's literally saying how far Sirius is from the Earth. I'm going to have to go for that it's going to be the distance, because the distance is also measured in parsecs, right? So I think that's going to be our D. Okay, I can't spell magnitude. I need to go in and fix that. So that's going to be our D. Same thing here. This is parsecs from the Earth, right? So this is going to be our D, but for the sun. Okay, our distance. There we go. Okay, so let's fill in our formula. So we now know the D is going to be 2.637. Now we got to get little m. Well, if you go back up here into the instructions, it says here that Sirius has an apparent magnitude of negative 1.44. So let's plug that in for little m. Okay, guys, go ahead and pull out your calculators. And I'll give you about a minute to plug this in, and let's see what y'all get. Oh, great. Okay, we're matching. Good. And we'll just say we'll round it in 3 decimal digits. Okay, great. Okay, so now we just got to do the same thing, but for the sun. All right, so m equals, what was its apparent little m? Negative 26.74 was its little m? Okay, so let's dissect this, because I don't think that's easy to plug into the calculator. Maybe it is for some of you guys, but I'm going to move the decimal place 6 times. So 1, 2, 3, 4, 5, 6. So it's really going to be that. Okay, if you want to just plug that into your calculator. And we still have to divide that by 10, which is going to make it even smaller by 1 decimal. So it looks like it's going to be point with 6 decimals. 1, 2, 3, 4, 5, 6. 4, 8, 8, 7. Okay, let's see what we get. Give you about a minute for that too. These aren't easy to plug in. I don't know, you guys. Is anybody else getting that? I moved it over 6. I moved it over 6. But then I knew that that was going to be going into to be divided by 10, because we put that right here. And so when I divide something by 10, it actually makes it even smaller and moves it another space. So that's why I moved it 1 more, was because of the dividing by 10. Okay, somebody else did get a 4.8. Okay, great. All righty, you guys. So let me, just because of clarity, because I did step skip, huh? That's no good. Oops. How can I, let me move this stuff out of the way. Now I can move this lower. Oh no, I just don't think this is going to happen. Okay, I'm just going to leave it. Too much work there. Okay. All righty, that finishes off for 3.